back to our technique of integration using substitution. I mean, you'll remember yesterday I said basically there's two techniques. So integration using substitution. Well, we talked about the standard integrals when we looked at it in extension 1. Now I want to talk about the non-standard integrals, I guess, the ones that they don't give you but are handy to know. And I've mentioned some of these already. So there's the du on root u, so that'll be 2 root u. Du on u squared, that's another one that comes up a lot. You end up with minus 1 on u. Log of x log x minus x. Tan we've talked about. I mean, I've left the absolute value signs off there, but log of sec, or of course you could go minus the log of cos. Sectan is sec. Now these last two here, these will come in very handy in extension 2 when we're looking at what we call quadratic denominators. The way I remember them, they're very similar if you look at them. In fact, they're basically the same if you look at them. The only difference is what's under the square root sign, but it matches what's under the square root sign. So you have the square root of the difference of two squares there, and the square root of the sum of two squares, and it works out to be the log of x plus whichever square root we're talking about there. So those three that I've asterisked there, on the original standard integral sheet that's over here, they used to appear, but now they're not on the new reference sheet, which leads me to believe that either they'll get you to prove it in order to use it, or they won't ask us a question where you have to use it. It makes me think that's what's going to happen now. But of course, I could be completely wrong. As I say, if you remember what they are, it's going to save some time. All right, let's have a look at this one. Here's the difference now. You'll notice I haven't written down what the substitution is. We have to come up with it. So different ways of coming up with substitutions. You see a square root sign. Very often the substitution is going to be what's under the square root sign. So u equals x squared plus 4. So there's our x squared plus 4. Du will be 2x dx. And there we go. We've got half of du. And ends up, well, add 1 to the power over the power. So half times 2/3 u to the 3 on 2. And subbing back in for the u, we get our answer. Well, we could leave it like that, I suppose, but no, it looks so much nicer. 1/3 x squared plus 4 root x squared plus 4. Of course, another way I could do it. If you notice you've got a root of the sum or difference of two squares, a trig substitution might be able to be used, because you can create a trig identity, and then you can get those two terms under the square root sign, turn it into one term squared, and then the square root of the square cancels out. So x squared plus 4, the one I'd want to use would be 2 tan theta, because then x squared will be 4 tan squared, and remember tan squared plus 1 is sec squared. Dx then would become 2 sec squared theta d theta. So subbing all that in, the x is 2 tan theta. The square root, as I just said, would be 4 tan squared plus 4. But 4 tan squared plus 4 is the same as 4 sec squared. And the square root of 4 sec squared would become 2 sec. But then the derivative is 2 sec squared theta. So tidying all that up, I'll get 2 times 2 times 2, which is 8. We've got the tan theta, but we'd have sec theta times sec squared, which is sec cubed theta. Right, now what do we do? Has that made life any easier for ourselves? Well, I can now rewrite that in terms of sine and coses, and I get sine theta on cos to the power of 4, but sine is, of course, the derivative, well, minus the derivative of cos. So I could do another substitution, u equals cos theta. Du is minus sine theta to theta, and so I end up with minus 8 du on u to the 4, which is negative 4, add 1 to the power over the power. So now I've got it in terms of u, sub the u back in, and I get sec cubed, because its power is negative 3, so the cos was on the bottom, became sec. That's still not back in terms of x. How do I get the sec theta back to x? Well, I'll draw myself a little triangle and go back to what we said. We said x was 2 tan theta. So we end up with x over 2 is tan theta, opposite over adjacent. Bit of Pythagoras. Not a coincidence, the hypotenuse ends up being the square root that we originally started with. So you'll find that the missing side will often be that same square root. But now I can read off. I know what sec is. So I get the square root of x squared plus 4 cubed, and we get the same answer. I am not suggesting that's a great way of doing it. Right? The first way is a much better way of doing it. I'm just saying, hey, look, there are different ways. You can choose different substitutions and they will work. Mind you, had you looked at that question and saw, oh, look, we've just got derivative times function, and because remember, you chose the substitution there in extension 2. They didn't give you the substitution, so you don't have to use substitution. You notice the derivative times function, you get it straight away. Okay, x root x plus 1. Here's one where I'm going to make the substitution the whole of the square roots. And so u will be the square root of x plus 1. Another way of thinking about that is x is u squared minus 1. Sometimes that makes substitution a bit easier. So dx will be 2u du. Now let's sub in. So x is u squared minus 1. The square root of x plus 1 is u. And dx is 2u du. Expand that all out. We get 2 lots of u to the power of 4 minus u squared. So add 1 to the power over the power. Now sub the u back in. U is the square root of x plus 1. Well, we could leave it like that. Look at that. Yeah, all right, most people will probably just leave it like that, but it looks so much nicer, don't you think? Another way, same question. X root x plus 1 dx. I can use algebraic manipulation. So try and create that factor x plus 1 out the front. Well, I've only got x. Well, I'll rewrite it as x plus 1 minus 1. And then break it up into 2 integrals, and it becomes x plus 1 to the power of 3 on 2 minus x plus 1 to the power of a half. And both of those I can now just add 1 to the power over the power. And we get the same answer. So in that case, possibly the algebraic manipulation is a better way to go than the substitution. Okay, let's have a look at this one. dx, 1 plus root x squared times root x. I don't know about you, but the first thing I'm seeing there is derivative times function. Do you see it? Because the derivative of root x is 1 on 2 root x. And so we've got the root x on the bottom. That's what jumps into my head. But if we did it by a substitution, all right, let's make u equal 1 plus root x. And surprise, surprise, there's the u, dx on 2 root x. So if you didn't notice it, all of a sudden it comes out with our substitution. But we've got limits, so we're going to need to fix those up. So when x equals 1, u will be 2. When x equals 4, u is 3. We end up with 2 lots of the integral from 2 to 3 of du on u squared. Now, a thing about substituting in. Separate your variables. That's the technique we use with it. You separate the variables before you substitute in. Never substitute in something like that. dx equals 2 root x du. Very tempting, because you go, oh look, so u times 2 root x. We'll sub in dx equals 2 root x dx, and oh, root x is cancelled. Horrible. You separate your variables. Okay? Now, and with the limits, if your new integral is with respect to u, then your limits has to be with respect to u. You don't leave the old limits on there. So it's a complete substitution. You've replaced every instance of x or things that refer to x. So the numbers refer to x, you need to replace those as well. All right, let's do the integration then. And there's that du on u squared. Remember I said, oh, that happens a lot. We get the minus 1 on u, sub in, there's our answer. Oh, well again, it's derivative times function, isn't it? But all right, we don't notice it. We'll make u equals sine x, du equals cos x dx. We need to change our limits. So when x is pi on 3, u ends up being root 3 on 2. And when x is pi on 2, we get u equals 1. So we end up with the integral from minus root 3 on 2 to 1 of u to the power of 5. Add 1 to the power over the power, sub in, there's our answer. Now let's have a look at this one. X dx on the square root of 25 minus x squared. Gosh, lots of ways we could do this one. I could create the derivative on top. I could do that. But seeing this is an exercise on substitution, oh, now I can see a couple of different substitutions. But look, difference of 2 squares. I could do a trig substitution. There's an option. Or I could just do 25 minus x squared. That's an option. Which way did I go? We've gone the 25 minus x squared. So du is minus 2x dx. Change our limits. So they become 16 and 9. So our integral becomes minus a half. There's that du on root u, which we know to be 2 root u. So a half times 2 is 1. And and I swapped the limits around as well. So that got rid of the negative sign. And so it's root 16 minus root 9, which is just 1. 25 minus x squared dx. Now, this one I can't create derivative times function. It's the same square root, mind you. So doing that substitution, 25 minus x squared, not going to help me with this one because I can't create the du. So this is one where that trig substitution could come in handy. So I'm going to make x equals 5 sine u. That'll get me 25 minus 25 sine squared, which I can change to 25 cos squared, and find the square root of that. You'll notice I've rearranged it over there and made it u equals the inverse sine of x on 5. Main reason I did that is because we've got to convert these limits, and I think that's an easier thing to work with to work out the limits. So dx is 5 cos u to u. So when x equals 0, we get the inverse sine of 0, 0. When x equals 5, we get the inverse sine of 1, pi on 2. So we have 25 minus 25 sine squared, which as I say is 25 cos squared. But then for the dx, we have 5 cos u to u. So all of that tidies up to be eventually 25 cos squared. But we have a technique to integrate cos squared. I can change the cos squared to be a half of 1 plus cos 2u. Now I can integrate, sub in the pi on 2, sub in the 0, 25 pi on 4. Okay, not a bad substitution. Here's another one. Hang on a sec. Square root of 25 minus x squared. I know that shape. It's a semicircle. And I'm just integrating from 0 to 5. So, it's just the area of a quarter of a circle. Oh, there you go, 25 pi on 4. Remember, if you recognise the shape and you've already got a formula, that's going to save you time rather than doing all the integration or working out which technique you need to use. The only exception, of course, is if they've tied your hands and said, do it by this method. Then, okay, you got it. But if they're simply saying, integrate this, you can do it whatever way you want. All right, so for C, and as I pointed out there, the difference with extension 2 and extension 1 is that the substitution is not necessarily given. Sometimes they still give it to you, but not always in extension 2.